Hello.
Hi,
How are you guys?
you're doing well.
Well, that's good. How's 118A so far going? This summer session.
I'm gonna be quite honest, I am taking it a second time.
Uh-huh.
I had
Yeah.
it first with Dr. Levens and she was a little rough for me.
Yeah. Uh-huh.
So
She's so fast-paced, right? Like she goes like did you take it over like fall or when did you take it?
it was actually winter of this year.
Yeah.
She was really sweet, but it's like it was just her lecture quizzes that really messed up.
Right, like the bi-weekly ones, right? Like every 2 weeks. Like it was very fast, huh?
Yes, and actually the 10-minute quizzes too, but I kind of realized I didn't have the right study methods. I still have like honestly, if I didn't really take the class like before, it didn't really, it would have like yeah, it would have been not good for me. So I mean, I'm glad I'm taking it again.
Uh-huh. Yeah, that's good. That's good. And was it a rough quarter for you that quarter, winter quarter? Like did you take other hard
Yes,
classes?
I mean it was I'm actually a transfer student, so like it was
Uh-huh.
just really hard adjusting,
Yeah,
and
right.
then I don't know.
Like,
What I'm glad about is that like we're gonna have Newman projections on Thursday, and then
uh-huh.
our main quiz on actually Tuesday is gonna be resonance.
Right.
So, so
On
resonance is like
resonance.
the only like thing I need help with, honestly. Like I'm okay with like drawing bond line structures, going from bond line to condense, and that I'm okay with. It's just resonance that I mainly
Uh-huh.
want to go over.
Yeah, okay, yeah. So that's what we can focus on. We could focus on a lot of resonance. Is there like a practice worksheet that she gave for resonance, like the quiz that we could go over? Um or we could go over like her notes. Here. Let's see. Resonance. Uh over here. Yeah. Yep. The separation rules 1, 2, 3. Yep. Okay. Yeah. So we could first go through her notes and then go through practice problems afterwards. But for resonance, it's basically the movement of electrons, right? And electrons are negatively charged, and they tend to go towards something that is positively charged, or something that is missing electrons, right? So when we look at this first example right here, we see that this nitrogen is triple bonded to this oxygen right here. Are you guys familiar with calculating formal charges from Gen Chem? Right. This oxygen here has a formal charge of +1 because if you look at the periodic table, it has 6 valence electrons. But we see that it has 1, 2, 3, 4, 5 electrons to itself. So when we have 6, which is its valence electrons, minus how many electrons it has to itself, 5, that's +1. That's why this oxygen here is positively charged. This nitrogen here is neutral because if you look at the periodic table, nitrogen on the periodic table has 5 valence electrons. And when we count how many electrons it has to itself, it has 1, 2, 3, 4, 5. So 5 minus 5 is going to be 0. That's why it's neutral, right? There's no formal charge there. And when you think of resonance, right, here's a tip. Move the negative charges, which could be in the form of a pair of electrons, right? Or it can be in the form of a double bond or a triple bond, right? They will go towards something positively charged, something that is missing electrons, right? Um, you could move it towards double bonds as well, but we see here that in this structure, we are moving one of the bonds of the triple bond to this oxygen atom right here, right? So that's why this oxygen here is going to gain a pair of electrons, right? Is this bond right here has 2 electrons, and those 2 electrons right there are these 2 electrons right here, right? That's why there's a double bond instead of a triple bond between the nitrogen and oxygen now, because one of the bonds came onto the oxygen as a pair of electrons. Now, when we calculate the former charge of this oxygen, it's now going to be 6 minus how many electrons it has to itself, which is 1, 2, 3, 4, 5, 6. Right, so 6 minus 6 is 0. It's now neutral, right? But this nitrogen right here is now positively charged because when we see its formal charge, like it has 5 valence electrons. It has 1, 2, 3, 4. 5 minus 4 is positive 1. It has a formal charge of positive 1, right? So the overall charge of the structure maintains the same, right? It's a positive charge. But there's 3 rules to determine what's the major resonance structure versus the minor resonance structure. The most important rule, right, for determining the major versus minor resonance structure is going to be the octet rule, right? Every single atom in the molecule has to have fulfilled the octet rule, right? Except for hydrogen. Hydrogen is gonna only want like 2 electrons, but every other atom will most likely want 8 electrons, right? And then the second one, if there are negative charges, the negative charges should be on the more electronegative atom, right? Because the more electronegative atom wants that negative charge. It can handle that negative charge better. Now, the third rule is going to be that the opposite charges, they attract each other, like positive charges attract negative charges. So opposite charges want to be near each other, right? Close together. Okay. And the most important rule here is the octet rule, right? The octet rule is the most important rule here. Now, thinking of that, we see that this nitrogen here does not fulfill the octet rule. It has 2, 4, 6 electrons, right? So this is the minor resonance structure. This is the major resonance structure, right? Because this nitrogen here has 8 electrons, 2, 4, 6, 8. This oxygen also has 8 electrons, 2, 4, 6, 8. It looks kind of weird because the positive charge is on the more electronegative atom here for the major resonance structure, but the octet rule, it overpowers that rule, right? It overpowers how the positive charge wants to be in the less electronegative atom. So that's why this is the major resonance structure, right? This nitrogen here is a 6-tet, right? Because it has 6 electrons. Okay. Now moving on to the next one right here. I'm going to draw it out like this because it's easier to see in bond line form. Right. So what she has for that example is this, where we have hydrogen like that, and then we have a negative charge right here. So this carbon here is negatively charged, and we can move this pair of electrons down to make a double bond between this carbon and this carbon, right? But when we do that, this carbon here is going to break its octet rule, right? It's going to have 1, 2, 3, 4, 5 bonds. That's way too many bonds. That's 10 electrons. So to conserve the octet rule, we're going to pop this double bond onto the oxygen right there. This bond right here has 2 electrons. So those 2 electrons are going to move onto that oxygen to give us this resonance structure here. And this double-headed arrow right here is a resonance arrow, showing that the resonance structure based of those arrows are this right here, right? Because before, this oxygen here had 2 pairs of electrons, 1, 2. But now in the new resonance structure, it has 3 pairs of electrons. And when we calculate the formal charge, right, oxygen has 6 valence electrons on the periodic table because it's on the 6th column. If we calculate how many electrons it has to itself, it has 1, 2, 3, 4, 5, 6, 7. 7 electrons to itself. So 6 minus 7 is going to be a -1 charge right there, right? So that is okay because the overall charge is -1, so that's good. But we see here that the negative charge is on the oxygen in this case, whereas the negative charge is on the carbon in this case. Before we look at charges though, let's make sure that every atom fulfills the octet rule. This carbon has the octet rule because there's like 2 hydrogens here from the CH2, so that's 2, 4, 6, 8 electrons. This oxygen has 8 electrons, 2, 4, 6, 8. This carbon here has 8 electrons, 2, 4, 6, 8. This oxygen here also has 8 electrons, 2, 4, 6, 8. So every atom here has the octet rule, so that's good. We don't have to worry about that. Now we look at the charge, the negative charge. The negative charge would be more stable at the more electronegative atom oxygen here, making this the major resonance contributor, right? So oxygen is more electronegative than carbon, so the negative charge should be on oxygen here. Okay. Now for this one right here, we use the same structure, right? But in this case, when we make a double bond right here, they do not pop the double bond onto the oxygen. They just create the double bond right there, right? And this right here is not good because this carbon right here has way too many bonds. It has 1, 2, 3, 4, 5 bonds. That's 10 electrons, right? That breaks the octet rule. And also another thing is that the overall charge of this structure is -1 there's no charge here that we see. So that's not good, right? Because our resonance structure, we have to maintain the same overall charge, right? So that's not good. This is the wrong structure, 5 bonds on carbon. So this is not even a resonance structure of this, right? That's not even a resonance structure. That's incorrect. Okay, now let's move on to the next one. So for this one right here, we use the same structure, right? Which is this negative charge. But instead of moving this pair of electrons to create a double bond here, we're going to move this bond, which has 2 electrons, onto the oxygen like that to give us this resonance structure right here. So there's a single bond now because we're moving one of the bonds of the double bond onto this oxygen, right? And this oxygen is now going to have a negative charge because before it had 2 pairs of electrons, but when we moved that pair of electrons onto the oxygen, it gained a pair of electrons, making it negatively charged. But now if we look at this carbon here, because this carbon here lost a bond and has 4 valence electrons, and we count how many electrons it has 1, 2, 3, 4 minus 3 is positive 1 charge. This is a positive charge right here. And whenever you see a positive charge on a carbon right there, that's what we call a carbocation in organic chemistry, right? A cation is something positively charged. Carbo is carbon. So when you see a carbon with a positive charge, we call that a carbocation, right? So this is technically a correct resonance structure, but it's very minor, extremely minor, right? Because of a couple of things, right? This carbon here does not have the octet rule. It only has 2, 4, 6 electrons. It's missing 2 electrons, so that's bad. Another thing is that we have a lot of charges around like that, right? And if you have a lot of charges around like that, that's unstable. We want to have the least amount of charges possible for a molecule to be stable. So this right here is the major resonance structure, right? And this one right here, less charges win, right? Less charges are more stable. And also this is a sextet, right? That does not fulfill the octet rule. Okay. Now if we look at this one right here, let me just draw it over here. Right, nitrogen is on the 5th column of the periodic table, so it has 5 valence electrons. If you calculate the formal charge of this nitrogen right here and count how many electrons it has 1, 2, 3, 4. So 5 minus 4 is positive 1 charge, like that. Okay, that's why it has a formal charge of positive 1. Now, if we calculate the formal charge of this one, it still has 5 valence electrons because it's the same atom, nitrogen. But when we calculate how many electrons it has to itself, it has 1, 2, 3, 4, 5, 6 electrons to itself. So 5 minus 6 is negative 1, right? That's why it's a negative 1 charge. Now, when you do resonance, think about that tip. The negative charges move towards the positive charge. So let's say we move one of the pairs of electrons on this nitrogen to create an extra bond there, to create a triple bond between this nitrogen and nitrogen right there, right? We would have to do something else. We can't just do that, right? Because if we do that and we don't do anything else, this nitrogen will have 5 bonds, right? 1, 2, 3, 4, 5. That breaks the octet rule. We don't want that. So to conserve the octet rule, we have to pop this double bond onto the carbon right there to give us this resonance structure here. And this bond right here has 2 electrons, and I want to draw those 2 electrons out as a pair of electrons like that on that carbon. And then there's a single bond now between this carbon and nitrogen. This is now a triple bond between them. Now let's calculate the formal charges. This carbon here has 4 valence electrons. When we calculate how many electrons it has to itself, it has 1, 2, 3, 4, 5 valence electrons. That's 4 minus 5, that's negative 1. So this carbon here has a negative charge like that, right? This nitrogen here has 5 valence electrons, but it has 1, 2, 3, 4. 4 electrons to itself. 5 minus 4 is positive 1. So this nitrogen here is going to be positively charged. Okay, now let's look at this nitrogen. This nitrogen, 5 valence electrons, but it has 1, 2, 3, 4, 5. 5 minus 5 is 0, neutral. So this is neutral right there. And that makes sense because if we calculate the overall charge of this, which is neutral, plus 1 minus 1 is 0, this resonance structure here is also neutral. Plus 1 minus 1 is also neutral, 0, right? So now we have to look at the difference between them. We see that both resonance structures has a positive charge on the middle nitrogen, so we could ignore that nitrogen atom. Before we look at charges though, let's think about the number 1 rule. right? Which is the octet rule. Let's make sure that every atom here has the octet rule. This carbon has 4 bonds, so that's good. This nitrogen has 4 bonds, so that's good. This nitrogen has 8 electrons, right? 2, 4, 6, 8, that's good. Let's look at this one. 2, 4, 6, 8, good. For this atom, 2, 4, 6, 8, good. This carbon, 2, 4, 6, 8, good. So every single atom in both resonance structures has the octet rule. So we can ignore that fact there. Now let's move on to the next factor, the negative charge on the more electronegative atom. The nitrogen here in the middle, we could ignore that because they're the same on both resonance structures, right? They have positive charges there. The difference is where the negative charge is at. We have a negative charge on the nitrogen on the left resonance structure. We have a negative charge on the carbon on the right resonance structure, right? And we know that nitrogen is more electronegative than carbon is because it's to the right of the periodic table and higher, or like it's to the right of the periodic table more so than carbon is. So this is the major resonance contributor because the nitrogen is able to hold onto that negative charge way better, right? So this is the major resonance structure here. Let's see what she says about that. She says nitrogen more electronegative than carbon. Okay, now let's move on to this one, carbon monoxide. So we have that carbon triple bonded to an oxygen, and then this oxygen here has 6 valence electrons, but right now it has 1, 2, 3, 4, 5 electrons to itself. 6 minus 5 is positive 1. So its formal charge is going to be positive charge like that. This carbon here has 4 valence electrons, but right now it has 1, 2, 3, 4, 5. So 4 minus 5 is negative 1, negative charge. Is that right? Let me see here. Yeah, negative charge like that. Okay. So what we can do is that because there's a positive charge on this oxygen right here, we could move one of the bonds of the triple bond onto that oxygen to make it neutral, right? We can make this oxygen neutral by giving it an extra pair of electrons. And its extra pair of electrons is going to come from one of the bonds of the triple bond right here. So I'm going to draw an arrow showing the movement of 2 electrons to go into that oxygen right there, giving us this resonance structure here. All right. So I could highlight it to make it more clear. Like this bond here has 2 electrons, which I moved over to that oxygen, which is now those pairs of electrons right there. Now, when we calculate the formal charge of this oxygen, 6 minus 1, 2, 3, 4, 5, 6 is 0. That's neutral. Okay. Now let's calculate the formal charge of this carbon here. 4 minus 1, 2, 3, 4. 4 minus 4 is 0. 0. So that's also neutral. Now, this is kind of tricky because you know how earlier we said less charges win, right? So it looks like this is the major resonance structure because there's no charges there, right? They're both correct resonance structures because the overall charges match up, right? This is overall neutral. Plus 1 minus 1 is 0. This is overall neutral because there's no formal charges. So some people would say this is the major resonance structure because they think of the less charges win factor, but do not forget about the number 1 factor for resonance major contributor, which is the octet rule. If you look at this carbon right here, we see that it only has 2, 4, 6 electrons. It's a sextet. This does not have the octet rule. Whereas this carbon here has 2, 4, 6, 8 electrons. Good, that's octet. That's 8 electrons, right? This oxygen also has 8 electrons. This oxygen also has 8 electrons. So the major resonance contributor is going to be this one here, not because of the charge rule. If we were just thinking about the charge rule, this would be the major one. But there's a more important rule, the octet rule. This is the major resonance structure because every single atom here fulfills the octet rule. All right, let's see what she says. Yep, this C here has a sextet, right? That C. Whereas this C here has the octet. That's why this is the major resonance contributor. Okay. Any questions on any of these before I give you guys random practice ones to work on and tell me which one's the major resonance contributor? Okay. When is your quiz? When are your guys' quiz? This Thursday?
Tuesday. We have
Tuesday.
one, yeah, twice a week on Tuesdays and Thursdays.
Did it start already, or like is the first quiz this upcoming Tuesday?
It's this Tuesday.
Yeah, and it's on residents only.
I think so.
And what is the one on Thursday?
I'm not sure.
You're not sure? Okay, yeah. Because I wanted to go over that as well because I'm doing these sessions every Sunday, so I wanted to go over Tuesdays and Thursdays like quiz content today. Okay, so let me just give you guys some practice problems here. This one here is gonna have 3 resonance structures that I want you guys to draw. And I want you guys to tell me what's the major resonance structure. And then for this one, this one right here is also gonna have 3 resonance structures. And I want you guys to tell me which one's the major one. And then for Thursday's quiz is counting pi bonds and hybridization. Okay, yeah, we could go over that today too. Yeah. What? Okay. Yes. This is good. Okay, trying to think of one more here. Let's do. Okay, so let's do. Actually, let me give you one more here so that we got that. Let me do this one. No, let's do nitrogen. Okay, let me see here. Okay. Okay, I'll leave this one for last. Okay, let's get started with the first one here. How can we get the second resonance structure? It's also Newman projections. Okay, we can go over Newman projections too. With the staggered eclipse, energy, torsional strain, gauge, steric hindrance, all those things for Newman projections. And the hybridization sp, sp2, sp3, and sigma bonds versus pi bonds after this resonance structure here. So what do you guys think we could do from this structure to get this second resonance structure here? What arrow do you guys think we could start off with? Like where can we start the arrow?
Moving the lone pairs.
Yep, the lone pair of electrons here, we could start the arrow there, and we can make a double bond right here by moving that lone pair of electrons over here to create a double bond between this carbon and this carbon. Do we have to draw any other arrows after that? Right.
You would move the other double bond.
Mm-hmm. Yes. And because I want you guys to draw 3 resonance structures, you could draw in 2 ways, right? You could move the double bond here and move the double bond over here. But because I want you to draw 3, we're gonna move this double bond onto that carbon right there, giving that carbon a pair of electrons, right? The reason why we have to move that double bond over there is because this carbon here has an invisible hydrogen bond, right? Because in bond line structure, the hydrogens are invisible. There is an invisible one there because we know this carbon is neutral, and for carbon to be neutral, it has to have 4 bonds. But right now, we only see 3 bonds explicitly. We see 1, 2, 3 bonds explicitly. So that means that there's an invisible hydrogen bond right there. So if we make a double bond between this carbon and this carbon right here, this carbon would break the octet rule if we don't do anything else, right? That carbon will have 5 bonds. 1, 2, 3, 4, 5. That's not good. So that's why we have to move this double bond onto that carbon right there to conserve that octet rule, right? So that would give us this resonance structure here. Like that, right? And this carbon here with a pair of electrons does have an invisible hydrogen as well. So if we calculate the formal charge of this carbon, that carbon has 4 valence electrons, but it has 1, 2, 3, 4, 5 electrons to itself. 4 minus 5 is -1. So this carbon here will have a negative charge like that. We said earlier that the carbon with a positive charge is a carbocation. A carbon with a negative charge is a carb anion. Right, there's no O, it's because we don't want 2 vowels next to each other. We drop the O because there's an A there. So a carbon with a negative charge is a carb anion. Okay, now from here, we could move this pair of electrons to create a double bond right here between this carbon and this carbon, and then we would move this double bond onto the oxygen to give that a negative charge, right? Giving us that resonance structure, and that's a negative charge because it gained a pair of electrons from this bond right here. And all of these are valid resonance structures because all of them have an overall charge of -1. But which one do you guys think is the major resonance structure and why?
The last one because it's on the most electronegative atom.
Correct. So you're thinking of charge here. The negative charge is on the most electronegative atom, oxygen. So that's a major resonance structure. But before we think of that, what's the most important rule that we have to be careful of that can sneak up on you on some tricky problems? What's the most important rule for determining major resonance contributors?
The octet rule.
The octet rule, right? So before we look at any charge, let's make sure that every single atom in all of these resonance structures fulfill the octet rule. And in this case, I'm just gonna tell you guys, it does fulfill the octet rule. Like every single atom here has 8 electrons, so we don't have to worry about that, right? So we can move on to the charge rule. We want the negative charge on the most electronegative atom, oxygen. So that's the major resonance structure there. That's good. Okay, so this is the answer, and the reason why is because we want the negative charge on the most electronegative atom. Okay, now moving on to the next one. This is basically the same thing as what we did here, but it's in a cyclic structure. So I'm just gonna draw the arrows here for you guys. I'm going to move this pair of electrons to create a double bond between this carbon and this carbon, pushing this double bond right here, right? This arrow starting from this double bond, which has 2 electrons, and I'm going to move it onto that carbon, giving it a pair of electrons like this. Okay, and then we can move that pair of electrons to make a double bond right there, pushing this double bond onto the oxygen like that, which is going to give us this resonance structure right here. Okay, and every single atom here of all of these resonance structures has the octet rule. So then the next factor we look at is the negative charge on the most electronegative atom, which is oxygen, making this the major resonance structure. Okay, so same thing as what we did earlier, but just a different structure, a cyclic structure. Okay. Okay. So for this one right here, I just want you guys to draw one resonance structure. How would you guys draw this resonance structure? What arrows would you draw? What arrows would you start off with?
Moving the lone pair from the nitrogen.
Yeah, we're gonna start from the lone pair of nitrogen and create a double bond right there. A common mistake that students make is that they try to make a double bond right there, like that, right? But we can't do that. You can't skip an atom like that, right? So when you move pairs of electrons, they can't jump across the atom, like they can't leapfrog across like that. They gotta crawl there, right? They gotta do it one atom by atom. So when we do this right here, this carbon here is gonna break the octet rule if we don't do anything else, because it's gonna have 5 bonds, right? So then we're going to move this double bond onto there, creating a double bond right there, giving us this resonance structure right here. Okay, now this nitrogen that had a negative charge is now neutral, because if you calculate the formal charge, right, nitrogen has 5 valence electrons, but when we calculate how many electrons it has to itself, it has 1, 2, 3, 4, 5. 5 minus 5 is 0. This carbocation here, right? So here's another thing. For exams and quizzes, if they give you formal charges, they do not have to give you like pairs of electrons or invisible hydrogen bonds, right? So what I mean by that is that they could just give you this as the structure, making the pairs of electrons on this nitrogen invisible. And they would expect you to know how many pairs of electrons are in this nitrogen if they give you the formal charge. And here's how you could determine how many pairs of electrons if they make it invisible. So we know that this nitrogen here has a negative charge, right? And that nitrogen has 5 valence electrons. So 5 minus x, that's how many electrons it has to itself, equals -1, right? The -1 here is this -1 charge that they gave us. So let's solve for x, right? So we could subtract 5 on both sides. -x equals -6, x equals 6, right? So this nitrogen here has 6 electrons to itself. But we see that this nitrogen explicitly has 2 electrons so far, right? So there's 4 invisible electrons that we do not see. And those 4 invisible electrons that we do not see are these 4 electrons here. 2 pairs of electrons, 2, 4, like that. So that's how you determine how many pairs of electrons are there on a atom that they don't give you. They don't draw it explicitly for you. Okay. So I'll just put this on the side. Then we do that. We do this. Get this resonance structure right here. Okay. Now, which one is the major resonance structure? Which one looks like the more major resonance structure? Yeah. Of course, of course. But it looks like on Wei's notes, right? She drew out all the pairs of electrons for you, which is nice. But on the exam, it could be a different story. Like on the exam, she could be mean and drop the pairs of electrons and make it invisible and just give you the formal charges. In case she does that, you could use this method, this technique. Okay, so the major resonance structure here is going to be the right one because there's less charges. Less charges win, right? We want a neutral molecule. Now, some people might ask, why didn't we draw these as the arrows? Make a double bond here, and instead of making a double bond right here between these two carbons, why can't we just do that? You can, right? And if you do, you'd get this resonance structure. Right, which technically is a resonance structure, and then from there you could make a double bond right there just like that to get this. So it just depends on like the exam, right? If they give you boxes, you know how many resonance structures to draw. That's good for Liebens class. And Wei, I don't know how her exams are like, but it looks like based on her notes, she does only want you to draw one resonance structure, so that's good. So you could just skip over this one right here, right? This one right here is the minor one compared to this one, right? Because they do have the carbocation here, we could ignore that, but the negative charge on the nitrogen is more stable than the negative charge on that carbon right there. Okay. Okay. Now looking at the next one right here. Oh, I gave you guys the resonance structure already. By accident, I forgot to erase this. But to get from here to here, how would you guys draw the arrows? Like, where would you start to draw the arrows here?
From the lone pair on the carbon.
Yeah, start on the lone pair of electrons on the carbon. Look where the negative charge is at, which is this. And then since we are only given one other resonance structure, we would have to move this double bond to create a triple bond there. And then move this little one and move it onto the oxygen right there, giving us this resonance structure here. Any questions on that before we move on? On how we got like the formal charges, like the negative charge on this oxygen, how the positive charge on this nitrogen maintain the same, right? And this is a valid resonance structure because the overall charge of this resonance structure is neutral, which is the same as this resonance structure. It's also neutral. Okay, now, based on that, which one is the major resonance structure and why?
The one on the right, due to the charge being on the more electronegative atom.
Yeah. Every single atom here has the octet rule. This nitrogen here has the positive charge, so we could ignore that. Then the only difference is this negative charge right here. But we see that the negative charge over here is on the more electronegative atom, which is more stable. So that's why this one here is the major resonance contributor. Nice. Okay. Now for this one right here, this one is a little bit tricky on where you would start the arrow and how you would move the electrons. Like when you move the bond onto the atom, I am confused on what happens to it, if that makes sense. The bond onto the atom. Oh, like when we're not making a double bond, something like this. Like let's say we have this, right? Like when we move this pair of electrons here and then we move this double bond onto that atom right there, like is that part messing you up? Is that part confusing? Delilah? The double bond onto the oxygen. Oh, the double bond onto the oxygen. Yes, this one right here. Okay. So this pair of electrons on the carbon right here is gonna make a double bond between this carbon and this carbon. That's how we got that double bond right there. This double bond right here, one of the bonds went over here to create a triple bond between the carbon and nitrogen. Right? But if we don't do anything else, that's bad because this nitrogen here will have 5 bonds. 1, 2, 3, 4, 5. To conserve the octet rule, we have to move this bond onto the oxygen, right? Where this bond here has 2 electrons. So let's do that trick. Do you know how many pairs of electrons are in this oxygen? It's invisible right now, but we see that it's neutral. There's no formal charges. And if it's neutral, how many pairs of electrons are in this oxygen right here? How can you figure that out? They're invisible right now. Right, we could do that math technique. Oxygen has 6 minus X. We don't know how many electrons it has to itself, but that is going to be equal to 0 because it has a formal charge of 0. When you solve for X is going to be 6, right? Because 6 minus 6 is 0. So we see here oxygen so far has 2 electrons to itself. So it has 4 missing or invisible electrons that we do not see. And those 4 invisible electrons are these 4 here, which are 2 pairs of electrons. Right? So now when we move this bond, which has 2 electrons, right? Because you could like erase that and see that bond as 2 pairs of electrons, like 2 electrons like that, 1 pair of electrons like that. We're basically moving this pair of electrons onto this oxygen here, which gives that oxygen 3 pairs of electrons. So now when we calculate the formal charge, 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1, giving this oxygen a negative charge, right? This extra pair of electrons here came from that bond right there, right? Because this bond has 2 electrons. Does that make sense? Yep. That's good. Okay. Does anyone know how to get started with this resonance structure? Like how to start the arrows? Okay. So this one here is a little bit more tricky because usually you're thinking of that negative charge moving, right? But we can't do that because if we move that pair of electrons to create whatever that bond is, quadruple bond, we can't move anything else, right? And that's very bad. This nitrogen here is gonna have 1, 2, 3, 4, 5 bonds. So we can't do that. What we gotta do is that we gotta use one of the bonds of the triple bond here onto that nitrogen. And we said earlier that each bond has 2 electrons. So we're going to give this nitrogen here a pair of electrons. Yeah. And now there's a double bond between that nitrogen and carbon. Now, if we calculate the formal charge of this nitrogen, nitrogen has 5 pairs of electrons. And we calculate how many electrons it has to itself right now. It has 1, 2, 3, 4, 5. 5 minus 5 is 0, neutral. Good. Now, let's look at this carbon. Carbon has 4 valence electrons. It has 1, 2, 3, 4 electrons to itself. 4 minus 4 is 0, neutral. That's good. Which one is the major resonance structure and why? And after this, we'll move on to pi bonds and hybridization.
The first one due to the octet rule.
Nice. This one was a tricky one. I tried to trick you guys, but you got it. The first one is the major one, right? Even though it has more charges because of the most important factor or rule for major resonance contributor, which is the octet rule. Every single atom here has the octet rule. Like even though this resonance structure here has less charges, like there's no charges at all, this carbon here does not have the octet rule. It's a sextet, right? 2, 4, 6. Not good. Right? Whereas this carbon here has 8 electrons. 2, 4, 6, 8. That's good. So this is the major resonance structure because of the octet rule. It's good. Okay, now let's move on to counting pi bonds and hybridization. Okay, did she go over that in these notes? Hybridization. Oh, she did right here. SP, SP2, SP3. Are there practice problems that we can go over with that? And then I could see how she tests it, and then I could create similar ones to her style. Let's see. Yeah, nomenclature. No, no infrajections, energy, acid base. Okay, okay. Okay. Let me go over leave-in stuff and teach you it that way. I had her previous quizzes, but I don't know where. Let me go to my other. No, I want the blank copy. I don't want the grid. Oh. No. I had some probably here. Yes, hybridization here. Okay, let's do this one. Okay. And pi bonds too. So before we go over that, let me teach you guys. This is probably a discussion thing. I don't think she went over this in lecture. Sigma bond and pi bond. So a sigma bond is going to be a single bond between two atoms, right? And they're going to have this shape right here. It's kind of like a dumbbell shape, and it has a overlap between them to show that bond right there. But a pi bond is going to be and this represents a single bond between two atoms. But let's say we have a double bond between those two carbons right there. That double bond right here is consisted of one sigma bond and one pi bond, right? One of the bonds are going to be this sigma bond right here, which is this direct overlap between those orbitals, right? Like sp2 orbitals. And then the pi bond here is going to be the dumbbell one, like this, right? And it has to be parallel to each other. They're not gonna directly overlap. They're just gonna have a parallel overlap, like that. And this parallel overlap here is the second bond, right? So one of the bonds of the double bond is a sigma bond, which is color-coded in blue. The double bond, like the second bond, is gonna be from the pi bond, which is this parallel overlap right here. And a single bond, right? They have free rotation, right? We could rotate this bond freely because when we rotate it, this direct overlap is still gonna be there, right? But this double bond right here has no free rotation. And the reason why it has no free rotation is because if we were to like rotate this bond, this parallel overlap would be broken, and then we would not have the double bond anymore. So that's why there's no free rotation in a double bond or triple bond. So now let's look at a triple bond between two atoms, right? A triple bond will have one sigma bond and two pi bonds. The sigma bond is the same, right? This direct overlap between this time sp orbitals. Hey, I'm going to show you guys that as well, like how to tell if an atom is sp hybridized, sp2 hybridized, sp3 hybridized. But now this time it has two p orbitals overlapping. So one set of p orbitals is going to be like that vertically, and then the second pair of p orbitals are going to be horizontal like that, and they're going to overlap horizontally like this. Now this is the strongest one, right? Because there's like a sigma bond and two pi bonds. So this even has less rotation, right? So this triple bond here has a sigma bond, which is in blue, one pi bond, which one of it is in pink, and another pi bond, which another one is in green, like that, right? The stronger the bond, the shorter the distance between these two atoms are, because they're forcing them together. So the triple bond is the shortest here, the single bond is the longest here, because the single bond is the weakest. Okay. Here's a conceptual thing though. Do you guys remember what is stronger? A sigma bond alone or a pi bond alone? Which one is stronger? Sigma bond, yes, because of this direct overlap. The pi bond is weaker because they're not directly touching. They're not directly overlapping, right? But a double bond is considered stronger than a single bond because it has both the sigma bond and pi bond added together, right? The single bond has no pi bonds at all. The triple bond is the strongest because it has a sigma bond and two pi bonds added together. So that's why that's the strongest one right there. Okay. Now, let's talk about sp3 versus sp2 versus sp. So in general chemistry, which like I kind of forgot a lot already, but like when you do like some, I don't forget what this is called, orbitals, right? The first orbital is like the s, and then this 3p orbitals. When you merge them together, you're gonna get sp3, right? One s and 3p orbitals like that. And because there's four of them, right? 1, 2, 3, 4. When an atom is sp3 hybridized, they're gonna have four sp3 orbitals, right? Because we have four of these orbitals. 1, 2, 3, 4. Okay. Now, let's say we have something that's sp2 hybridized. sp2, 1, 2, 3. Combine them together, that's 3, right? 3 sp2 orbitals and one 1p orbital, right? Now let's talk about sp, right? If we talk about sp, we're gonna have two sp orbitals and two unhybridized p orbitals like that. Okay, so let's look at some examples here. Let's just look at this random alkane in bond line structure, right? This carbon here is neutral, and because it's neutral, it has 4 bonds. But right now we only explicitly see 2 bonds, 1, 2. So that means it has 2 invisible hydrogen bonds, which are these 2 invisible hydrogen bonds right here. When we see 4 bonds like this, right, think of sp3 hybridization, where there's 4 of them, 4 sp3 hybrid orbitals, right? Because we're combining all of these orbitals together like that. And one of it is going to be right here, second one is going to be right here, third one is going to be right here, fourth one is going to be right here, and they're going to overlap with some other orbital, creating that bond right there. Okay. Now, let's talk about, let's say if we have a double bond right here. If we have a double bond right here, let's look at this carbon right here. This carbon has one invisible hydrogen because it's neutral, but right now we explicitly see 3 bonds. The one invisible bond is the one invisible bond to hydrogen. And because it has 3 bonding groups, 1, 2, 3, right? It's going to be sp2 hybridized, right? Where there's 3 of them, 3 sp2 hybrid orbitals are here, 1, 2, and 3. And because we said earlier that if it's sp2 hybridized, we have 1 p orbital, right? And that 1 p orbital is used to create a double bond with this carbon here, which is also sp2 hybridized. Now, if you have a triple bond, right? This carbon here has 4 bonds. There's no invisible hydrogens on this carbon because we explicitly see it's 4 bonds here, 1, 2, 3, 4. And this right here is going to be sp hybridized, right? It has 2 sp orbitals, 1 here and 1 there. And that means it has 2 p orbitals, 1 here to create like one of the other bonds of the triple bond there, and then another one here to create the 3rd bond of that triple bond for this triple bond right there. So this is sp hybridized, this is also sp hybridized. Right, so we could say this is sp3, sp3, sp2, sp2, sp, sp. There's 1 pi bond here. There's 2 pi bonds here. Any questions on that? Okay, so now the next thing that I'm going to go over here is going to be so Nasiri. I don't know if you guys heard about her, but she used to be the organic chemistry professor here at UC Davis. And Levens, they teach this differently, right? Because let's say we have a carbon double bond oxygen. We see that this carbon here has 3 bonding groups, 1, 2, 3. So that's an indicator that that carbon is sp2 hybridized. This oxygen here is also sp, like it looks like it has 3 bonding groups, 1, 2, 3. So it also looks sp2 hybridized. But I think Levens calls it P. So I gotta look at Way's notes on what she calls that. Did she go over this yet? This content, this concept? But I know for sure, like the hydrogens, right? Let's say, like we look at this hydrogen right here. This is S hybridized right there, right? This is 1 s orbital. Okay. Another thing which is probably the trickiest part about this content is this right here. If you have an amine like this, and it has 3 bonding groups, 1, 2, 3. I mean 4 bonding groups, 1, 2, 3, 4, and it cannot do resonance. This is sp3 hybridized, right? But now, if you look at this case right here, where there is a carbonyl, which is a carbon double bond oxygen nearby this nitrogen right here, we see that this nitrogen with a pair of electrons can do resonance with that carbonyl, giving us this resonance structure here. Right? Overall charges do match up, so they're valid resonance structures. And now if we look at the bonding order of this nitrogen here, or like how many bonding groups it has 3. 1, 2, 3. So in this resonance structure, it's sp2. In this resonance structure, it looks sp3. The one that's going to overpower the other is going to be the sp2 hybridization if it can do resonance. The reason why is because if it's sp2 hybridized, that means it has 1 p orbital to create this double bond, to create that pi bond, right? And we want to be able to create that pi bond for resonance. And resonance is a stabilizing factor. It makes molecules more stable. So if it can do resonance, it's going to do resonance. making this nitrogen sp2 hybridized, right? So the difference here between this and this is that this is sp3 because that pair of electrons cannot do resonance, whereas this nitrogen here is sp2 hybridized because this pair of electrons here can do resonance. Any questions on that concept? This is probably the trickiest one for this material. Okay, now let's look at this problem here. Let's look at, give the hybridization at the indicated atoms sp, sp2, sp3, unhybridized s, or unhybridized p. Let's look at A. Is A sp, sp2, sp3, unhybridized s, or unhybridized p? A is this one. sp2, right? Because it has 3 bonding groups, it's a double bond. sp2, we'll check the answers afterwards. How about B? This nitrogen atom here.
SP3.
sp3, because there is an invisible pair of electrons there, because if you see it's neutral, but it has 1, 2, 3 electrons explicitly, so it has 2 missing electrons that we do not see, which is that 1 pair of electrons. But this 1 pair of electrons here cannot do resonance, right? And because it cannot do resonance, it's going to be sp3. Correct. Nice. What about C?
SP3.
sp3, because there's 4 bonding groups, there's 2 invisible hydrogens, so that's sp3. How about D?
SP2.
So D right here is a carbon that is triple bonded. And when you see a carbon that's triple bonded, think of it being sp, right? Because that carbon will have 2 sp hybridized orbitals and 2 unhybridized p orbitals, right? Its 2 unhybridized p orbitals are going to be blue and green, right? To create those 2 other bonds right there. So another way you can think about it is that this carbon here has 2 bonding groups, 1 here and 1 here. And it has 2 bonding groups, and that's going to be sp hybridized, right? So a triple bond, think of it being sp. Okay, now E, we didn't really go over this, but that's unhybridized s. F is sp2 because it has a double bond and has 3 bonding groups, 1, 2, 3. G is a halogen, so it's gonna be unhybridized p for Levin's terms. I don't know about Wei. I'm gonna have to see her notes for that. H, what do you guys think H is gonna be? This nitrogen atom here.
SP2 since it's near an oxygen.
Yeah, sp2, right? Because it's right next to this carbonyl, like carbon double bond oxygen here, and it could do resonance. And because it could do resonance, it's going to be sp2. It looks sp3 because it has 4 bonding groups, right? As it's drawn. 1, 2, 3, 4. 4 bonding groups, sp3. But it's not sp3 because we see that it could do resonance with the carbonyl, the carbon double bond oxygen. And when it can do resonance, we said earlier, it's going to be sp2 over sp3. Okay? Now, how many pi bonds are there in this overall structure? 1 double bond is 1 pi bond, 1 triple bond is 2 pi bonds.
9.
9. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 9. Right. Okay. Now, what is the approximate bond angle on C? Like, this goes back to general chemistry VSEPR theory. Like, if it's sp3 hybridized, what geometric shape does it have, and what like preferred bond angle does it have for C?
109.5 and it's
Yep.
tetrahedral.
Correct. 109.5 degree tetrahedral. D.
180 and it's linear.
Yep. 180 degree linear. F.
120 and it's trigonoplanar.
Correct. 120 trigonoplanar. Nice. Okay. How many lone pairs? Oh, so these are the invisible lone pairs. A. That's gonna be 0 because A is a carbon that is neutral. So it has 4 bonds, but right now we only see 1, 2, 3 bonds explicitly. So its missing bond is the invisible hydrogen bond right there, but there's no pairs of electrons on A. Now, how about B? We talked about this earlier, right? Because this nitrogen is neutral. 5 minus X is 0, so that means X is 5. But right now we see it has 1, 2, 3. 3 bonds, 3 electrons to itself. So that means it's missing 2 electrons. And the 2 missing electrons are the 2 invisible electrons right there. So be careful of the question here. It's asking for lone pairs. So there's 1 lone pair. 1 lone pair is 2 lone electrons. Right? So there's 1 lone pair of electrons on B. E, that's a hydrogen. So that's 0. G, how about G? How many lone pairs of electrons are on G?
3.
Yeah, 3. Correct. 3 lone pairs of electrons because this bromine is neutral and has 7 valence electrons. So 7 minus X is 0 because that's a formal choice of 0. So X has to be 7. But right now we only see 1 electron to itself. So there's 6 missing ones. And those 6 missing ones are these 6 missing ones here. 1, 2, 3, 4, 5, 6. Right? 1, 2, 3 pairs. 3 pairs of electrons. Nice. Which of the above indicated atoms has delocalized electrons? So these ones here are asking like which one of these can do resonance, basically. Yeah, it's gonna be H. That lone pair of electrons can do resonance with the carbonyl. F. And A. Right, because they could do resonance around. Right, delocalization, like resonance. Another thing to talk think about resonance here is that if you have a network of adjacent p orbitals, they can do resonance, right? So that could be sp2 or sp3 or sp2 or sp3, right? So they're gonna be adjacent to each other, next to each other. So sp2, 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 sp2. This one here, sp2, sp2, sp2. This one here, sp2, sp2, sp2. Okay. And for something to be delocalized, they need to have at least 3 adjacent p orbitals for it to be delocalized. Okay. Let's look at the key really quick. Practice exams. This one, yep. This one, yep. SP2 AFH, yeah. 0103, 0103, 109, yeah. SP2, SP, SP2P, SP3, SP2, yeah, we got all of them correct. Okay, any questions on this before we move on to Newman projections? Okay, so Newman projections. They're just a way of viewing the molecule. So let's say I have this structure here. And let's say this is you looking through the molecule directly at that atom right there. Right? This is your eye looking at this molecule at this angle. So you're looking directly at this carbon right here. Okay. So this carbon here that you're looking at is going to be this dot right here. Okay. This carbon here is attached to a methyl group. So let's draw that methyl group out like that. It's attached to 2 invisible hydrogens. So I'm going to draw those 2 invisible hydrogens out like that. And because you are right here looking at this carbon directly, you do not see this bond right here. Right? This bond is hiding behind this carbon, behind this dot right there. You don't see that bond. Right? The carbon behind it, right, which is this carbon right here, is going to be represented by a big circle like that. Right? So I could color code it to make it more clear. This pink circle right there is this pink carbon right there. This blue dot right here is this blue carbon right there. And you cannot see that bond. Right? Because you're directly in front of this blue carbon, which is what you're seeing right here. And then that blue carbon is attached to a methyl group and 2 invisible hydrogens, which are these hydrogens right here. And then behind it is this pink carbon right here, which is attached to an isopropyl, a methyl, and an invisible hydrogen. And notice how I'm drawing out the bond coming out off of the circle, not this dot right here. Does that make sense so far? Okay. So now we can rotate this single bond right here that we cannot see, right? Because it's a single bond, it has free rotation. And when we do that, we're gonna have to keep one carbon stationary, right? And the carbon that I'm gonna keep stationary is this blue carbon here. So this right here is gonna stay the exact same. It's not gonna move at all, right? But I'm gonna move the groups on the pink carbon around, and I'm gonna move it 60 degrees, right? So I'm gonna move it clockwise. So I'm gonna move everything in this direction right here. And when I do that, I'm gonna get this structure here. Right, so that is the exact same copy and paste of whatever the blue carbon has. This methyl group here is now gonna be right behind that hydrogen. This isopropyl group here is gonna be right behind that hydrogen. And then this hydrogen here is gonna be right behind this methyl group right there. Okay, we could rotate it 60 degrees again. So when we rotate it 60 degrees again, I'm gonna keep everything on the blue carbon the same. Do not move that, which is that. The pink carbon, right? Hydrogen here, methyl here, isopropyl there. Okay, any questions on this so far, on how I got like these Newman projections so far? On how I rotated it 60 degrees clockwise? Right, this methyl group here is this methyl group. This isopropyl group here is now here. This hydrogen is now here. Right, I'm just rotating it 60 degrees clockwise again. Okay, I could do that one more time. Everything on the blue carbon stays the exact same. Copy and paste. The carbon on the back is pink. The isopropyl is now right there. The hydrogen is now right here. This methyl is now right there. And then I could do it actually one more time here. Everything on the blue carbon stays the exact same. So this is going to be hydrogen, hydrogen. This is a pink carbon on the back. Isopropyl right here. Hydrogen right here. Hydrogen right here. Right? Okay, now I want to show you guys the terms. Before I show you guys the terms, let's focus on the blue carbon, which is attached to a methyl group and two hydrogens. The bulkiest group on that blue carbon is that methyl group, because the methyl group is bigger than the hydrogen. So I'm going to highlight it like that. Now, if we look at the pink carbon right here, we have an isopropyl versus a methyl versus a hydrogen. And the bulkiest group compared to all those three atoms is going to be this isopropyl group right here. Notice how the two bulkiest groups here, right, are 180 degrees apart from each other. They're far away from each other as possible. This is called the anti-configuration. They are anti to each other. They're opposite to each other, right? That's good. That's very good because they're not bumping into each other, right? When they're close to each other and they bump into each other, that's called steric hindrance, right? Steric hindrance is a term where portions of the molecule bump into each other, and that's not good. That makes it less stable. And when you have more steric hindrance, you have less stability. When you have less stability, you have more energy. All right, and these can come in the form of questions like which one of these Newman projections has the higher energy, or which one of these Newman projections has the highest stability, something like that, right? Now you notice how every single group here is 60 degrees apart. That's called the staggered configuration, right? They're staggered from each other, so they are staggered. If you look at this one here, where they're like on top of each other, like 0 degrees apart from each other, this is the eclipsed configuration. And that eclipsed configuration has torsional strain, which makes it less stable, more energetic. Now, if you keep tracking the highest, like the bulkiest group, which is this methyl group here, and the isopropyl group here, if they are like next to each other, like creeping on each other like that, right? They're not anti to each other, but they're creeping on each other, next to each other like that. That's the Gauss configuration. So the Gauss configuration has steric hindrance because they're bumping into each other a little bit, right? So that increases steric hindrance, increasing the energy, right? Because it's decreasing the stability, making it less stable. Okay, and then this one is eclipsed. This one right here is probably the least stable, right? Least stable, highest energy, because the two highest or two bulkiest groups here are right next to each other, eclipsed, right? So a lot of steric hindrance, a lot of torsional strain, right? This one right here is staggered because the two bulkiest groups here are Gauss to each other, right? They are staggered and right next to each other. If the two bulkiest groups are right next to each other in a staggered configuration, that's the Gauss configuration. Okay, I know that was a lot and it was pretty quick, but I want to do a Kahoot with you guys really quick on this concept. Any questions before we do that? When you say behind, does it matter if I write the group on the left or right of the group in front? Like this or this? Like in the eclipsed configuration, like if you drew the hydrogen here or here? Yes. So it doesn't matter as long as you're consistent. And what I mean by that is that notice how I rotated this methyl group 60 degrees here, and I just made it on top of the hydrogen, right? So like you could say to the left of it, this isopropyl group here would have to be on top of it like that. Now, if I were to draw the methyl group like below it, right, like on the bottom, then I would have to move the isopropyl group there as well to be consistent with that. So it doesn't matter as long as you're consistent with the other groups. Yeah, of course. Okay, let's do a quick Kahoot and end the session here. SNI hybridization. Newman projections. Oh, let's skip the relative acid strength because we didn't go over that, and then let's just do the Newman projection ones. Okay. Okay. Anyone else want to join? Starting in 10. Oh, the heck? Why is it so loud? Okay. Okay, let's if you guys know this one, answer it, but we didn't go over this, so you guys should skip this. If you guys don't know it. Nice. Yes. You guys know it. Nice. There's different factors, different rules for determining acidity. Yep. Yeah. I'll go over these later when I go over acid-based stuff, but let's get to the Newman projections. I'll just say the factor, and then when you guys go over the recording, you guys can figure out why. Right, the reason why that was more acidic is because of the hybridization. That was SP hybridized rather than SP3. And the more S character you have, the more acidic it is. SP2 has more S character than SP3. This one right here is going to be about the electronegativity factor, because if you deprotonate the carboxylic acid and you get that negative charge, they can do resonance equally, right? The only difference is about the electronegativity of the atoms nearby, like the inductive reasoning, right? Fluorine is more electronegative than bromine, so fluorine is able to pull on the negative charge better, stabilizing it more, making it a more stable conjugate base, weaker conjugate base, which is why B is the more acidic molecule. Okay. Okay, Newman projections. So this one here, it's a little bit hard to see, but it's eclipsed because the two groups are like on top of each other, 0 degrees. I know it's kind of hard because these are the quizzes or exams I had when I took OChem, like over COVID, like the lockdown season. So this was like the eclipsed version, right? The staggered is going to be more like 60 degrees, more equally spaced apart. So for this one, the two alkyl substituents, the isopropyl on the first carbon that we see directly, and the propyl group on the back carbon, the second carbon, right? They're eclipsed to each other, right? They're not staggered. The anti and gauche configurations are only on staggered configurations. And because this is not in its staggered configuration, it's neither anti nor gauche, right? They're eclipsed. Okay. Yes. So for this one, right? When we talk about energy and stability are inversely related, meaning that the more stable a molecule is, the less energy it has. The less stable a molecule is, the more energy it has. So the highest energy configuration is the least stable, is the most unstable molecule, right? And if we look at the top carbon, right, the bulkiest group of the top carbon is an isopropyl group. If we look at the back carbon, the bulkiest group of the back carbon is a propyl group. And we notice that the bulkiest groups here are eclipsing each other 0 degrees apart on top of each other. So that increases a lot of steric hindrance. They're bumping into each other. That's very bad, very unstable. They're eclipsing into each other. That's a lot of torsional strain. That's also very unstable. And because of that, the two bulkiest groups right next to each other, eclipsing and like on top of each other like that, a lot of steric hindrance, a lot of torsional strain. This is the least stable molecule configuration. This is the most unstable configuration, which has the highest energy, right? So the answer here would be red, highest possible energy rotamer, right? The lowest possible energy rotamer is the most stable molecule, and that's the anti-configuration, where both of the groups would be like in staggered configuration, opposite to each other, 180 degrees away from each other. That's the most stable molecule, aka the least energy configuration. Yeah, this one, yeah, it's kind of hard to say, but just think about if they're equally spaced apart or not. Or if you see any anti stuff, right? This one is eclipsed, right? Because they're not 60 degrees away from each other. They're not equally spaced away from each other. They're like on top of each other. The R groups or the alkyl substituents are and keep in mind these are eclipsed. This is an eclipse structure, not staggered, right? And because it's an eclipse structure, we cannot have anti nor gauche, right? Anti or gauche can only be staggered. This is not staggered, so it can't be anti or gauche, right? Anti is when the two bulkiest groups are opposite from each other, 180 degrees away from each other. Gauche is when the two bulkiest groups are right next to each other, but in a staggered configuration. But because this is not staggered, it's neither. Okay. Yes. So for this one right here, it wouldn't be the lowest possible energy rotamer because the lowest energy possible rotamer is the most stable molecule, right? This is not the most stable configuration because the most stable configuration would be the anti one. Anti configuration. This is not anti, right? If you look at the propyl group, it's not directly 180 degrees from the isopropyl group. They're eclipsed, right? This is an eclipse structure. So this is going to be in between, right? Because this is also not the highest energy rotamer. This is not the most unstable rotamer. The most unstable rotamer would be if the two Bogius groups are eclipsing each other, if they are like touching each other, right? So it's in between the highest and lowest rotamer. Okay, this one right here is staggered. This is the first staggered one that we've seen. Oh shoot, that was wait, that was the question. What the heck? Oh no. Yeah, this is staggered because the previous ones were eclipsed, like they were at a weird angle, but this one is staggered because every group is equally spaced apart, 60 degrees from each other. Yeah, so this is staggered. It's good. Now before we move on to the next questions, what's the bulkiest group on the top carbon that we see? On the direct first carbon that we see, what's the bulkiest group coming out of that dot? The propyl group, yes. The 3 carbons coming out of that single center dot. Correct. Nice. How about the back carbon, the circle? What's the bulkiest group there? Isopropyl, yes. Okay, keep that in mind because you're gonna look at the relationship between those two bulkiest groups to determine if it's anti-gauche or neither, if it's eclipsed, right? Yes. So for this one right here, the anti-configuration would be if the propyl group of the first carbon and the isopropyl group of the back carbon are anti to each other, 180 degrees apart from each other. But they're not 180 degrees apart from each other, right? They're not opposite from each other. The hydrogen is 180 degrees apart from the propyl group, and then the hydrogen is 180 degrees apart from the isopropyl group. But the anti one would be if the isopropyl group is 180 degrees apart from the propyl group, right? But you notice how the propyl group and isopropyl group are 60 degrees away from each other, right next to each other in a staggered configuration? That's the Gauche rotamer. That's the Gauche configuration, right? Which has steric hindrance. Okay. Okay. Think about what the highest possible energy rotamer is, and think about what the lowest energy rotamer is. And if it's not any of those, then it's gonna be in between, right? This is not the lowest energy rotamer because this is not the most stable rotamer. This is not anti, right? The least stable energy rotamer, right? The least energy rotamer is the anti rotamer. And because this is an anti, this is the least stable one. This is also not the highest energy rotamer because they're not eclipsing to each other, right? The two bulkiest groups are not eclipsing on top of each other 0 degrees. So this is in between, right? Like the highest possible energy rotamer is the most unstable one, which is when they're on top of each other. The bulkiest group on top of each other. The least energy one or the most stable one is the anti one. Because it's not any of those, it's in between. This one here is staggered because they're 60 degrees apart from each other. They're equally spaced away from each other. They're not on top of each other, right? Yes, so this one right here, the alkyl groups are the propyl group of the first carbon and the isopropyl group of the back carbon. Notice how they are 180 degrees apart from each other, right? They're kind of slanted like that. Like the isopropyl group is like right here, and then the propyl group is right here. They're 180 degrees apart from each other. They're not like vertical like that. They're slanted, but they're still 180 degrees apart from each other, making it anti. Right? And because it's anti, it's the most stable rotamer. There's least steric hindrance, they're not bumping into each other, and there's no torsional strain. So because it's the most stable rotamer, it has the least energy. Right? The highest energy represents the most unstable, and that's the one where they're eclipsing on top of each other. The two bulkhead groups right next to each other, 0 degrees apart from each other. Right, so that's kind of tricky. Like think about the stability versus energy. They're like opposite from each other, right? This is the most stable one, aka the lowest energy one. Okay, nice. Any questions on that before we end the session? And I hope that was helpful, guys. Let me stop the recording and see you guys someday.